Something extraordinary may have just happened on Mars. Something that could rewrite everything we thought we knew about life beyond Earth. NASA's Perseverance rover has detected strange chemical patterns inside a Martian rock, the kind that, on Earth, often point to living organisms. Scientists are cautious, but excitement is building. Could this finally be real evidence of life on Mars? Or just another cosmic false alarm? When NASA's Perseverance rover touched down in Jezero Crater back in 2021, its mission was clear: search for ancient signs of life hidden within Martian rocks. Scientists believed this crater once held a vast lake fed by rivers that carried clay, minerals, and sediment. Exactly the kind of environment where simple microbial life could have thrived billions of years ago. But no one expected that a discovery this intriguing would appear so soon. As Percy continued exploring the fractured edges of an ancient river channel, its instruments detected something unusual, a type of sedimentary rock unlike anything it had analyzed before. At first glance, it resembled ordinary Martian mudstone, dry, cracked, and battered by ages of dust storms. But when the rover zoomed in, the rock revealed tiny dark spots arranged in strange circular patterns. They were so small, they could easily be missed by the naked eye, yet they carried enormous scientific weight. These formations, nicknamed Leopard Spots by mission scientists, were rich in organic compounds. Carbon, phosphorus, and iron clustered together in rings only a fraction of a millimeter wide. On Earth, similar structures often form where water once flowed, especially in environments that supported microbial metabolism. The presence of these compounds didn't just hint at water, they hinted at chemical reactions often associated with life. Using its Pixel and Sherlock instruments, Perseverance performed a detailed chemical scan of the rock's surface. Pixel detected a combination of elements commonly found in clay-rich deposits formed in ancient lakes. Sherlock, a device designed to search for organic molecules, found patterns that were anything but random. The dark outer rims of the spots were enriched with iron and phosphorus, while the inner region blended seamlessly into the host rock, suggesting that whatever caused these rings acted locally and deliberately. On Earth, this specific combination, organics, minerals altered by water, and localized iron reduction, often signals microbial activity. Microbes can metabolize iron, transforming its chemical state as part of their survival process. When these changes become preserved in sediment, they leave behind patterns almost identical to the ones Percy observed. Still, NASA scientists know the dangers of jumping to conclusions Mars has fooled us before. False positives, misleading chemical reactions, and exotic geological processes can mimic signs of life. That's why the team approached the discovery with a mix of excitement and caution. They began testing every non-biological explanation: volcanic heat, strange chemical reactions, changes in acidity, anything that could create such formations without involving biology. Yet as experiment after experiment failed to fully explain the chemistry of these spots, something became clear. This rock was different. It was compelling. It demanded attention. And if its secrets could be uncovered, it might be the closest humanity has ever come to answering the question that has haunted us for generations. Has life ever existed on Mars? As Perseverance's instruments continued scanning the mysterious rock, mission scientists realized they were witnessing something far more complex than a simple mineral oddity. The chemical fingerprints inside these tiny leopard spots didn't just look unusual, they defied what we would normally expect from Martian geology. Element by element, the composition revealed a story that echoed processes we see on Earth, but almost never without life. The first clue came from the iron-rich outer rims surrounding each spot. When Pixel mapped the distribution of elements, it showed zones where iron had shifted from its oxidized state, iron 3, to its reduced form, iron 2. This is exactly what happens when certain microbes metabolize iron in low oxygen environments. On Earth, bacteria like Geobacter survive by consuming iron 3 oxides and releasing iron 2 as waste, leaving behind chemical halos similar to what Percy detected. These iron reduction patterns weren't random. They were consistent, localized, and tightly arranged, almost like chemical footprints left behind by something that once interacted with the sediment when it was still wet. The rover also identified phosphorus tightly bound within these outer rims. Another hint, since phosphorus is a key ingredient used by cells to store and transfer energy. Even more compelling were the organic molecules detected by Sherlock. These carbon-based compounds weren't scattered loosely throughout the rock. They clustered precisely within the dark outlines of the spots on Earth. Organics like this often bind to mineral structures formed in the presence of water, especially in environments that once supported microbial activity. And while organics alone don't prove life, their arrangement within these rings was difficult to dismiss as coincidence. Yet, NASA's scientific method doesn't allow for easy answers. Before considering life, they had to rule out every non-biological pathway. Could something other than microbes create these patterns? The first hypothesis was heat-high temperatures, especially from volcanic or hydrothermal activity, can cause minerals like greigite and vivianite to form. If ancient Martian groundwater had been heated by magma beneath the surface, that could theoretically explain the reduction chemistry. But Perseverance found no signs of nearby volcanic structures, no fractures, no deposits, nothing to suggest intense heat had ever touched this region. The surrounding rocks told a story of cold, ancient waters, not scorching underground reactions. The next possibility was acidity. Acidic water dissolves iron and sulfate ions more readily, raising the chances of purely chemical reductions. If Jezero Crater once contained highly acidic lakes, perhaps these spots formed without life. But then Percy made an unexpected discovery, a nearby fragment of olivine, a mineral that dissolves rapidly in acidic conditions. Its survival implied the environment wasn't acidic at all. Whatever formed the leopard spots, acidity wasn't the culprit. Researchers then explored a third option: slow, abiotic chemical reactions involving organic matter. But these processes require enormous energy and temperatures far higher than what the surrounding terrain ever experienced. And even then, they don't typically create such sharp, neatly defined mineral boundaries one by one. Every geological explanation collapsed under scrutiny. Each chemical clue seemed to point back to processes that, at least on Earth, are strongly associated with life. Still, even with mounting evidence, scientists hesitated because acknowledging what these patterns might mean forces us to confront a profound possibility that life, not recent but ancient, may have once metabolized iron in this very rock billions of years ago. But before anyone could make that claim, one final question remained. If not life, then what? What force on Mars had the power, precision, and chemistry to leave behind such unmistakable signatures? The answer would require deeper investigation and bring us closer than ever to a threshold humanity has never crossed. If scientists hoped to crack the mystery of the leopard spots, they needed to start with the most conservative approach. Assume life had nothing to do with it. This is how planetary science works. Begin with the null hypothesis and only abandon it when every alternative collapses under evidence. And that's exactly what the research team did. They tried to prove the rock was completely non-biological. The first suspect was greigite, an iron sulfide mineral known to form in environments where sulfur undergoes reduction. On Earth, microbes often drive this process, but it can also occur through volcanic activity. If underground heat or sulfur-rich vents once interacted with Jezero's ancient waters, greigite might have formed purely through chemistry. But Perseverance's instruments found no supporting evidence, no volcanic layers, no hydrothermal veins, no cracks or mineral structures indicating that scorching water ever flowed here. The whole region was geologically quiet, cold, stable, and undisturbed for billions of years. Without heat, the volcanic hypothesis fell apart. The next possibility involved chemical reduction of sulfate ions by organic matter. This process can occur without life under the right conditions, but only at temperatures above 150 to 200 degrees Celsius. Yet every measurement Percy took pointed to the opposite. The rocks preserved minerals that would have been destroyed by such heat. Their structure instead suggested long, slow interactions with mild groundwater. Again, the environment simply didn't match the chemistry. Then came the hypothesis of acidity. Acidic water dissolves iron and sulfate more easily, making reductions possible even without biology. But this idea collapsed the moment Perseverance detected a fragment of olivine near the sample site. Olivine is fragile in acidic conditions. It dissolves fast. Its presence meant the water wasn't acidic enough to trigger those reactions. What Percy found should not exist in a low acidity landscape unless something else caused it. Piece by piece, every abiotic explanation crumbled. None could account for the precise distribution of iron reduction, the clustering of organics, the mineral textures, or the geological context. The more scientists tried to separate life from the equation, the more the evidence resisted. But rejecting non-biological causes doesn't automatically confirm biology. It simply narrows the path. And now the path was pointing towards something extraordinary, a chemical imprint that, on Earth, almost always indicates microbial life. Still, scientists remained cautious. They needed one more piece of the puzzle, and Perseverance was about to provide it. By the time Perseverance finished its first round of scans, the research team realized they were standing at the edge of something profound. The chemical story told by the Leopard Spots didn't line up with any known geological process on Mars. But science demands more than patterns. It demands a mechanism. And this is where the mystery took a dramatic turn. Inside the rock, Percy detected early hints of two minerals that almost never form without the influence of specific environmental conditions: vivianite and greigite. On Earth, both are strongly associated with microbial metabolism. That doesn't mean they require life, but the way they form is deeply linked to the chemistry of living systems. Vivianite is an iron phosphate mineral that commonly appears in river sediments, wetlands, and oxygen-poor environments rich in organic matter. When microbes metabolize iron, they release iron too into their surroundings. If phosphate is present, and it was on Mars, this reaction naturally produces vivianite. Greigite tells a similar story. It often forms in environments where sulfate-reducing microbes break down sulfates into sulfides, which then bind with iron. But the real shock wasn't the minerals themselves. It was where they were found. They weren't randomly scattered through the rock. They were precisely concentrated in the dark outer rims of the Leopard Spots, exactly where iron reduction and organics converged. This wasn't just chemistry happening anywhere. It was chemistry happening in a confined, localized environment, as though something had once been interacting with the sediment in a structured way. Scientists began testing every non-biological scenario again. this time focusing on vivianite and grisite. Could these minerals form without life? Yes, under specific conditions: high heat, fluctuating acidity, or intense chemical reactions involving organic matter. But none of those match the environment of Jezero. No volcanic heat, no evidence of hydrothermal systems, no signs of acidic lakes, no fractures or mineral alterations caused by temperature extremes. Instead, everything pointed back to a quiet, stable ancient lake, cool, neutral, and remarkably Earth-like. Still, the team remained skeptical. They needed a way to break the tie between biology and chemistry. And that's when Perseverance spotted something small, green, and extremely important: a fragment of olivine. Olivine is a fragile mineral. In acidic water, it dissolves rapidly, breaking down into softer silicate structures. The fact that olivine was still intact meant the environment at the time these spots formed wasn't acidic enough to drive abiotic reduction reactions. This single rock fragment punched a massive hole in one of the last chemically plausible explanations. With acidity ruled out, the remaining geological interpretations weakened even further, but the rover's findings weren't limited to minerals. Percy also detected complex organic molecules, carbon-based compounds arranged in patterns that, on Earth, often point to biological origins, not simple carbon chains that rain down from space or form through random chemistry, but more structured compounds tightly bound to specific mineral features inside the Leopard Spots. NASA knew better than to label them as life. Organics can form abiotically, and Mars has plenty of ways to create them. But their arrangement, with phosphorus, iron, and water-altered minerals, felt eerily familiar. Then came an even more startling realization. The chemistry inside the rock resembled processes that occur in Earth's wet sediments, swamps, deltas, and shallow bodies of water where microbial communities thrive. Ancient Mars had similar environments billions of years ago. If life ever existed there, these would have been the ideal habitats. But interpretations needed clarity. Patterns can mislead. So the research team asked one final question: could the environment have simply mimicked biological chemistry? To answer that, they compared the Martian data to dozens of terrestrial samples in nearly every Earth analog. The combination of organics, water alteration, iron reduction, and phosphate enrichment pointed directly to microbial activity. There were no known cases where identical patterns formed without some biological participation. This didn't prove life, but it raised the stakes dramatically. In the end, the scientists reached a cautious but striking conclusion. They could not find any purely chemical explanation that accounted for everything Perseverance detected. Every geological pathway broke down. Every abiotic scenario conflicted with the data. Every test pushed the evidence closer toward one extraordinary possibility. The rock in Jezero Crater might hold the first true biosignature ever discovered on another world. But proving it would require something Mars could never give them: experiments far more precise than any rover can perform. And that meant only one thing: the rock had to come home. If the strange chemistry inside the Leopard Spots truly represents a biosignature, then humanity stands at the threshold of one of the most important discoveries in scientific history. But for all the remarkable instruments Perseverance carries, there is a limit to what a rover on another world can prove. The question of life, real ancient life, requires tests so sensitive, so specific, and so detailed that no machine on Mars can perform them. To solve this mystery, scientists need something incredibly rare: a piece of Mars brought safely back to Earth. This is the goal of the Mars Sample Return mission, an ambitious multi-stage effort designed to retrieve the cores Perseverance has already collected. Among those cores lies the piece of mudstone containing the Leopard Spots, now known as the Sapphire Canyon sample. Inside that small tube of rock may be the clearest evidence of extraterrestrial life ever discovered. Bringing it home will require 3 separate spacecraft, one to collect the samples, another to launch them into Martian orbit, and a third to ferry them back across millions of miles to Earth. It is a mission more complex than Apollo, more delicate than any Mars landing, and more expensive than any planetary project NASA has attempted in decades. But the reward, a definitive answer to whether life once existed on another planet, could rewrite everything humanity knows about biology, evolution, and our place in the universe. If the sample reaches Earth, scientists will conduct 2 key analyses. The first is chirality, the molecular handedness of amino acids. On Earth, life overwhelmingly prefers left-handed structures. If Martian organics show a similar bias or even a different consistent bias, it would strongly suggest biology. The second is carbon isotope ratios. Living organisms process carbon in predictable ways, leaving chemical signatures distinct from non-living processes. If Sapphire Canyon carries those same isotopic fingerprints, that would push the evidence toward a level of confidence humanity has never reached before. But even if the sample reveals no life, the discovery still matters. Mars preserves geological history in a way Earth never could. Without plate tectonics, erosion, or oceans reshaping its surface, Mars acts like a time capsule, storing information from an era when Earth itself was young. Understanding Martian chemistry, even non-biological chemistry, helps scientists reconstruct how planets evolve, how conditions for life emerge, and how rare or common habitable environments might be throughout the universe. Yet we can't ignore the possibility that the Sapphire Canyon sample may prove something extraordinary. If the rock truly contains evidence of ancient microbial activity, then life didn't just arise once here on Earth. It arose twice on 2 neighboring planets in the same solar system. And if life can spark in 2 places so close together, then the universe may be far more alive than we ever imagined. Maybe life didn't begin here. Maybe it came from Mars. Or maybe both planets were seeded by something older, deeper, and far more cosmic than we understand. Whatever the answer is, the truth is now locked inside a small cylinder sitting on the surface of Mars, waiting for the chance to come home. And when it does, humanity may finally learn whether we have ever been alone. If you enjoyed this breakdown, make sure to like the video, subscribe, and turn on notifications. Every week, we uncover the hidden stories shaping our universe, discoveries that challenge what we know, and reveal just how close we may be to answering humanity's biggest question: